Hello, viewers. In today's session, we are going to discuss another important problem from differentiability of functions. So, in this class, we are going to discuss the differentiability of this function f of x at this point x is equal to 0, where f of x is defined as x times tan inverse of 1 over x, where x is not equal to 0 and f of x is equal to 0 when x is equal to 0, right? So here we have to see whether this function f of x is differentiable at this point x is equal to 0 or not. So for testing the differentiability of a function at a given point, we have to find out the right hand derivative and the left hand derivative, right? So here we'll see how we'll find the right hand derivative and left hand derivative using the concept of limits. So let us start. Now suppose we have a function, say y is equal to f of x, which is defined in some domain D, and suppose we wish to test the differentiability of the function at some point x is equal to a belonging to this domain D. Then we have to find out the right hand derivative and the left hand derivative. Now, if the right hand derivative and the left hand derivative both exist and they are finite and they are equal to each other at x is equal to a, then we can claim that the function is differentiable, right? So the condition for the existence of derivative of a function at some given point, the right hand derivative and the left hand derivative must be equal to each other, right? So let us here find out the right hand derivative and the left hand derivative of this function at x is equal to 0, and let us see whether both these derivatives are equal to each other or not. So now the right hand derivative is defined by this limit, that is limit, here we have h tends to 0 and f of a plus h minus f of a divided by h. So this limit gives us the right hand derivative, and the notation for the right hand derivative is given by f prime, and here we write a and here we put a positive sign, right? So this limit is it gives us the right hand derivative. So in this case the value of a is 0, so a is equal to 0, and here the function f of x is defined as x times tan inverse 1 over x for all x not equal to 0, but for x is equal to 0 we have f of x is equal to 0. So when x is equal to 0, f of x is given as 0, so this implies that f of 0 is equal to 0, right? So the value of the function at x is equal to 0 is equal to 0. So now we have a limit h tends to 0, and the value of a is 0. So here we have 0 plus h, and here we have f of 0 divided by h, and here we have f prime of 0, and here we have a positive sign, right? So let us evaluate this limit. So we have limit h tends to 0, this is f of h, 0 plus h is h, f of 0 is 0, because here f of x is equal to 0 for x is equal to 0, and here we have h. So now we have a limit h tends to 0, f of h over h, right? Okay, now we have to evaluate this limit. So let us find out the value of f of h by replacing x by h. So we have here h, then we have tan inverse 1 over h, and here we have h, right? So f of h is obtained by replacing x by h in this function. So now we have this h and this h get cancelled. We have limit h tends to 0, and here we have tan inverse 1 over h. So now we have to evaluate this limit. Now see here h is tending to 0. So when h tends to 0, then 1 over h, 1 over h tends to infinity. So here this limit is now equal to tan inverse infinity, because when h tends to 0, 1 over h tends to infinity. So now this limit is equal to tan inverse infinity, and we know that tan pi by 2 is not defined, that is infinity. So we can now replace tan inverse infinity by pi by 2. So here we have pi over 2. So the right hand derivative of this function at x is equal to 0 is equal to pi by 2. So here we'll write the right hand derivative equal to pi by 2. So let us now find out the value of left hand derivative. Now the left hand derivative is defined by this limit, that is limit h tends to 0. Here we have f of a minus h minus f of a divided by minus h, and here we write f prime, and here we have a and we put a negative sign over a, right? So this limit gives us the left hand derivative. So here the value of a is 0. So we have now a limit h tends to 0, f of 0 minus h minus f of 0 divided by minus h. So this is limit h tends to 0, and we have f of minus h. 0 minus h is minus h. F of 0 is 0, and here we have minus h. So this is limit h tends to 0, f of minus h over minus h. So now we have to evaluate this limit. Now to get the expression for f of minus h, we have to replace this x by minus h in this expression, right? So we have limit h tends to 0, and we have here minus h. For x we have minus h, and then we have tan inverse 1 over minus h, and in the denominator we have minus h. So now this minus h and this minus h get cancelled. We have limit h tends to 0, and we have tan inverse of minus 1 over h. So now from inverse trigonometric functions, we know that tan inverse of minus theta is equal to minus tan inverse theta. So here for theta we have 1 over h. So we can now write the left hand derivative is equal to limit h tends to 0, and we have minus tan inverse 1 over h, right? So tan inverse minus theta is equal to minus tan inverse theta. So now, as we have discussed earlier, when we have calculated the value of right hand derivative, when h tends to 0, then 1 over h tends to infinity, right? And we have now here we can write this negative sign in front of limit notation. So we have limit h tends to 0, tan inverse 1 over h. So now we have minus tan inverse, and here we have infinity, right? And tan inverse infinity is pi by 2, so we have minus pi by 2. So the value of left hand derivative is equal to minus pi by 2. So viewers, we have obtained the value of right hand derivative as pi by 2 and left hand derivative equal to minus pi by 2. And from this discussion, we see that the right hand derivative and left hand derivative are not equal to each other. That is, pi by 2 is not equal to minus pi by 2, right? So here, although the right hand derivative and left hand derivative both exist and they are finite when x is equal to 0, but these two derivatives are not equal to each other. Hence, we can claim that this function is not differentiable at x is equal to 0, because for differentiability of a function, both these derivatives must be equal to each other. So finally we can say that this function f of x, that is equal to x times tan inverse 1 over x when x is not equal to 0, and f of x is equal to 0 when x is equal to 0, is not differentiable at x is equal to 0.